Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. So students, today we are going to discuss about the module Conducting Polymeric Materials from the paper Functional Materials. The main points which will be covered in this module are: we will be studying the commonly conducting polymeric materials such as polyacetylenes, polythiophene, polyphenylene vinylenes, polyanilenes, polycarbozoles. Their structure, their properties, and various applications are discussed in detail. So let us start with a brief introduction about this module. Polymers have always been considered as the insulators of electricity. No one would have believed that polymers could conduct very good as the metals. But now such feats have been achieved, and that though through a simple modification of ordinary organic conjugated polymers called as electrically conducting polymer, or we can say as synthetic polymers. These materials combines the electrical properties of metals with the advantages of polymers such as lighter weight, greater workability, resistance to corrosion and chemical attack, and obviously the lower cost. And finally, they also have infiltrated our day-to-day life with a wide range of products, ending from most common consumer good to highly specialized applications in space, aeronautics, electronics, and obviously the non-linear optics. It is therefore no wonder that polymers are called as the materials of 21st century. The first breakthrough in the field of electrically conducting polymers took place around 1978 when it was demonstrated by Shirakawa et al. That polyacetylene or PA, an intrinsically insulating organic conjugated polymer, exhibits dramatic increase in electrical conductivity on treatment with oxidizing agents, or we can say that electron accepting or reducing agents which are electron donating. These oxidation and reducing reactions which induces highly conductivity in PA are termed as P-doping and N-doping respectively. Polyacetylenes. Polyacetylene or PA is a material of historic importance because its synthesis in thin film and the discovery of chemical doping by Shirakawa, Heeger, and MacDiarmid to massive advances in the area of conductive polymers followed the development of plethora of devices based on those materials. Today, one can make devices based on conducting polymers which range from displays, transistors, solar cells, batteries, and sensors. Polyacetylene is one of the simplest polyconjugated polymers which consist of the repeating unit of a single bond CH double bond CH single bond N. First polymerization of acetylene was achieved by Natta and co-workers using a Ziegler-Natta catalyst, yielding a polymer that was gray-colored, infusible, that is unable to melt or fuse, and it was a powdery substance. Irrespective of what the form of Pa is, the chain have a due to strong pi conjugation between the sp2 hybridized carbon atoms in its chain. Strong interactions between the chain cause a rigidity in the structure consisting of pi-stacked polymer chains, causing above attributes. This material was not soluble in any of the common solvents. This substance was not easy to characterize and has poor electrical properties. Subsequently, the researchers tried several other catalysts to polymerize the acetylene, which yielded similar products. The below figure shows the cis and the trans polyacetylene. Polyacetylene. It is electrically a semiconductor with electrical conductivity being in the range of 10 to the power minus 9 to 10 to the power minus 5 Siemens per centimeter. The conductivity can be tailored by chemical doping, leading to the variations of over 14 orders of magnitude. A mechanically stretched and highly aligned Pa can exhibit electrical conductivity of the order of 10 to the power 5 Siemens per centimeter after iodine doping, which is nearly comparable to that of highly conductive metals such as copper and gold. PPV or polyphenylene vinylene. Polyphenylene, which is also termed as PP, is shown in the figure, is another conducting pi conjugated polymer which attracted substantial research attention as it can be tailored into various derivatives which can be engineered optical and electrical properties. One of the most important derivative of polyphenylene is polyphenylene vinylene or PPV, which is a conducting polymer of the rigid rod polymer family. The schematic representation of PPV is also shown in the figure. Although the material was first synthesized in 1960, the research on this material received a significant boost in 1990 when electroluminescence was discovered in the material. Subsequently, work was devoted to study the changes in the functional groups on the properties of PP, the absorption and the emission characteristics of PPV-based polymers in visible spectrum of the light are highly tunable by what is used as a functional group. Now, the thin films of PPV with high degree of crystallographic orientation possess a P14 symmetry. The structure is made of a monoclinic unit cells which consist of two monomer units. PPV is basically a diamagnet and possess very low electrical conductivity. The electrical conductivity of PPV can be made to increase by doping with the substances such as iodine, alkali metals, acids, or ferric chloride. However, doped materials are rather less stable, leading to faster degradation, particularly in thin films form. The unaligned and unsubstituted form of PPV shows only moderate conductivity with doping. Higher conductivities can be expected in the alkoxy-substituted PPVs, which are generally easier to oxidize than the parent PPV. Longer the side chains are, lower the conductivity, which is very difficult to interchain the hopping of charge carriers. PPV is the only polymer of rigid rod family that can be processed into a highly ordered crystalline thin film. PPV and its derivatives are electrically conducting upon doping. Although they are insoluble in water, its precursors can be manipulated in aqueous solution. PPV thin films without any chemical substitution exhibit the bright yellow-green colored fluorescence. The rather they having small optical band gap and its bright yellow-green fluorescence make PPV an attractive material for applications in devices such as light-emitting diodes and organic photovoltaic devices. PPV materials without the appropriate solubilizing substituents are difficult to process, and thin films are typically prepared via precursor routes. Generally, two approaches are used for synthesizing the PPVs. First is called as the Wessling method, and the second is the Gilch method. In Wessling approach, silene-sulfonium salts are reacted with an equal molar amount of the base, leading to the formation of soluble precursor polymer. This precursor polymer is then thermally treated to yield the conjugated PPV. In Gilch method, RR dihaloperoxylenes is treated with the potassium tert butoxide in organic solvents. Alkyl or alkoxy substituents on the aromatic ring are sometimes used to enhance the solubility of PPVs. So students, the next polymer which we are going to discuss is polythiophenes. Among various pi-conjugated polymers, polythiophene and its derivatives have been studied very extensively for their properties as well as their integration in device forms. Polythiophenes are polymerized form of various thiophene units, a sulfur heterocycle. Some of the forms of polythiophenes are schematically shown in the below figure. The basic mer unit is the sulfur-containing heterocyclic compound with the formula C4H4S called as thiophene. The polythiophene polymer is formed by linking the thiophene units through its 2,5 positions. Due to the rigidity of their conjugated structure, unsubstituted conjugated polythiophenes are difficult to process and analyze as they are generally insoluble and infusible. However, one can fabricate useful form by substituting thiophenes at the 3 and 3 and 4 positions. Polythiophenes. Now students, we are continuing a discussion on polythiophenes. Polythiophene become conducting when the electrons are added or removed from the conjugated pi orbitals via doping, as shown in the figure below. For example, some examples of poly-3-dodecylethiophenene when doped with iodine can exhibit the conductivity as high as 1000 Siemens per centimeter, which is only about 2 orders of magnitude lower than that of copper. However, in general, one cannot achieve the conductivity as high as this, which is also not desirable for intended applications such as solar cells. Polythiophenes. Among various dopants used, iodine and bromine can yield high conductivities, but they are unstable and slowly evaporate from the material. On the other hand, use of organic acids such as trifluoroacetic acid, propionic acid, and sulfonic acids yields polythiophenes with rather lower electrical conductivities. However, the environmental stability of these compounds is superior. Oxidative polymerization using ferric chloride results in the formation of poly-3-alkylethiophene such as poly-3-hexylethiophene. So, one of the derivatives of polythiophenes, which is a p-type doping, poly-3,4-ethylene dioxythiophene, which is the P dot, is extensively used as an electrode material, example in capacitor electrodes. One of the best example of the developments in the regular polythiophenes is the synthesis of head-to-tail poly-3-alkylethiophene 2,5-diol, whose development has led to various studies of the molecular assembly of pi-conjugated polymers studied extensively for solar cell devices. Next type of polymer which we are going to discuss is polypyrols or PPY. Polypyrrole is an organic polymer which is formed by polymerization of the basic unit called as pyrrole The schematic representation of polypyrrole is shown below. The undoped form of polypyrrole is an insulator with a band gap of nearly 4 electron volt. Upon doping, the band gap reduces to about 2.5 electron volt and the material becomes an electrical semiconductor due to the removal of pi electrons from the upper section of the valence band. The polaron and bipolaron in polypyrrole extends to 3-4 monomer units of the polymer chain. Polypyrrole is typically amorphous and is chemically insoluble in many solvents, and as a result its characterization is quite difficult. Polypyrrole can be prepared either via an oxidatively chemical process or electrochemical polymerization of the monomers of pyrrole. First report on the synthesis of polypyrrole appeared in 1963 by Weiss, which showed the pyrolysis of tetraiodopyrrole to produce the materials that are highly electrically conducting. One needs to dope the polymer polypyrrole to achieve a conducting polymer, which is typically achieved by the oxidation of the polymer, that is by p-type doping. The films, now in the case of p-type doping, the process can be carried out electrochemically, which helps in achieving the high purity conducting films of the polymers easily. The films deposited on the electrodes are immersed in the electrolyte. Their thickness and composition can be controlled quite easily by varying the process parameters such as voltage, current, concentration, etc. Thin films of undoped polypyrrole have a yellow color which becomes darker upon the exposure to oxidizing such as doping conditions, leading to blue or black films depending on the degree of polymerization as well as film thickness. Doping also tends to render the polypyrrole brittle. Also, both undoped as well as doped films have no solubility in the common solvents. So students, now let us discuss the attributes and various applications of polypyrroles. First we'll discuss the attributes. It has good environmental stability, ease of synthesis, and higher conductivity. The various applications are sensing applications as biosensors and gas sensors, anti-electrostatic coatings, solid electrolytic capacitors, electrochromic windows and displays, packaging, polymeric batteries, electronic devices. Polyaniline or PANI. Polyaniline is commonly known as PANI, is one of the most studied conducting polymer due to its high electrical conductivity and rich chemistry it offers. Polyaniline is a conducting polymer belonging to semi-flexible rod polymer family. It was first synthesized in 1862 by Letheby when he carried out the electrochemical oxidation of aniline in the sulfuric acid. Further studies carried out during 1910 to 1912 led to structure predictions. These works led to the identification of a molecular sequence in Pani consisting. Pani was first synthesized in 1862 by Letheby when he carried out electrochemical oxidation of aniline in the sulfuric acid. Further studies carried out during 1910 to 1912 led to the structure predictions. These works led to the identification of a molecular sequence in Pani consisting of alternate amine and imine as well as benzenoid and quinoid moieties. Also, it was found that there could be fluctuations in the oxidation states of Pani. The further work on Pani remains nearly absent until about 1960s when it was reported that Pani becomes substantially electrically conducting when it was exposed to protonic acid in its stable half oxidized or half reduced form, commonly known as emeraldine base. So the conductivity in the polyaniline arises because of delocalization of the segregated semi-quinone radical cations along the main polymer backbone. Now this figure shows the basic polyaniline structure where N plus M, the small n and the small m, equal to 1, and X is the half degree of polymerization. Now students, we are continuing the discussion on polyaniline. The interest in Pani was further rejuvenated in the mid-1990s when MacDiarmid and Epstein identified a new process to make polyaniline even more electrically conducting. They termed this process as secondary doping. This type of doping of polyaniline films led to a large increase in their crystallinity, which was retained even after the solvent was completely evaporated, along with the reduction in the viscosity of the material in the solution form. Polyaniline is also relatively inexpensive than the other polymers. It has 3 distinct oxidation states in its neutral base form. First is leucoemeraldine, which is whitish or colorless, emeraldine, that is emeraldine salt, which is green, and emeraldine base, which is of blue color. And third is per-nigrin aniline, which is blue or violet colored. Among these 3 states, the oxidation state corresponding to the blue colored intermediate emeraldine base is the most stable under ambient conditions. On the other hand, leucoemeraldine base and per-nigrin aniline base oxidation states results from the reduction and oxidation respectively of Eb. The LB state is characterized by colorless or yellowish form in aerobic environments, which further develops a light green tint when it is slowly oxidized. The unique aspect of polyaniline emerge upon the exposure of EB state or emeraldine state oxidation state to strong acid, inducing the formation of green emeraldine salt form of polyaniline. This form exhibits the electrical conductivity up to 10 orders of magnitude higher than its unprotonated counterpart. Protonation of polyaniline helps to delocalize the otherwise trapped diminoquinone diaminobenzene state. Emeraldine base is considered as the most useful form of polyaniline as it is highly stable at room temperature. Also, when it is doped with acid, the resulting emeraldine salt form is highly electrically conducting. Although it is not easy to explain the structure of emeraldine base or the salt form of polyaniline, some of the experimental works suggest that the structure is built up of semi-quinone radical cations which are separated by individual units of Mers. The conductivity in polyaniline arises because of the delocalization of these segregated semi-quinone radical cations along the main polymer backbone. So students, they can be note that this statement has been previously explained also. Early works on Pani on the small molecules such as use of small molecules acids, example sulfuric acid or hydrochloric acid, were employed as a dopant to give rise to the formation of emeraldine salt state of polyaniline. Now, polyaniline has a response to both the acid or the base, making it useful for acid or base sensing applications. Polyaniline is also useful for applications related to the flexible electrodes due to its softness, anti-static coatings, as well as for electromagnetic shielding applications. Now, the change in the color of polyaniline associated with different oxidation states can be exploited in the devices such as sensors and electrochemical devices where the color changes is an important parameter. Now, electrochemical potential of polyaniline is between copper and silver, with it is nobler than the copper and slightly less noble than silver. So, because of this, it is also useful in printed circuit board for the corrosion protection as well as to provide the final finishing. Polycarbazoles. The basic unit of polycarbazones is carbazole unit, which is nothing but an aromatic heterocyclic compound which offers several positive attributes for applications as a conducting polymer. The basic unit is based on the structure of an aromatic heterocyclic organic compound, indole. The difference is that in carbazole, the second benzene ring is fused onto the 5-membered ring at 2,3 position of indole. Some of them are the low-cost 9H carbazole and the fully aromatic nature of the unit, leading to a better chemical and environmental stability. Besides, from the chemistry basis, one can easily replace the nitrogen atom with a wide variety of functional groups. These substitutions allow the tailoring of its optical and electrical properties as well as its stability. Also, bridged biphenyl unit in structure leads to lower band gap. The two important derivatives having carbazole units in the main backbone are poly-3,6-carbazole S and poly-2,7-carbazole S. Due to their tunable optical and electrical properties, these are potential candidates for applications in optoelectronic devices such as organic photovoltaics, organic field effect devices, and light-emitting diodes. Polycarbazole also exhibit or emit the strong light in the blue region and high fluorescence quantum yields. They also show excellent hole conduction characteristics as well as high thermal stability. Their energy levels can be well aligned with that of ITO, making hole injection easier, governed by the nature of substitution and whether it is 3,6 or 2,7 type. Very often, researchers prefer the use of poly-2,7 carbazoles in comparison to 3,6 carbazoles, as former exhibits high fluorescence quantum yields in the solution form. The poly-2,7 carbazole also exhibit extended conjugation over several monomer units, which is an outcome of rigid polyparaphenylene motif connected via nitrogen atoms. The electrical conductivity of poly-3,6 carbazole is higher than the poly-2,7 carbazole. But on the other hand, it is easier to synthesize the poly-3,6 carbazole than poly-2,7 carbazole, as former has better solubility in the common solvents because of flexible polymer structure. So students, let us summarize what we have learned in this module. First, polyacetylene sparked the initial work on conducting polymers. Second, amongst subsequent candidates, polythiophene are extremely adaptable. They can be modified and shows properties which are suitable for various electronic and optical devices. Third, polypyrols are another class of conductive polymers which are used in applications such as sensors, capacitors, and packaging. Lastly, recently the polycarbazoles have emerged as exciting materials, especially due to their prospects for organic solar cell applications. Thank you.